Let's go to Octave, where we have various codes. So let me run this Octave, and I am going to show you 4 codes today. First of all, the code B that we have, here we will see the frequency domain representations and time domain representation of AM signal. Then we have NBFM, and then we have WBFM. In code number C, we will study in code number C, we are going to study this frequency multiplier. So this is a code for frequency multiplier implementation. And in code number D, we will have an implementation of frequency mixer. So I'm giving you the basic codes today for frequency multiplier and mixer. Applied to various situations, like in code number E, we will be applying frequency mixer to the case of DSB-SC, and in code number D, we will be applying it to NBFM, right? This NBFM. And by using these codes, you will be able to generate this complete system. So I am only giving you the codes for these blocks. And by combining these blocks in various orders, you can generate this complete system at a desired frequency that you want. And it is very important to understand them. So let's begin by code number B. In code number B, what are we going to do? In code number B, we are going to do frequency modulation, that is actual frequency modulation equation versus NBFM. This is what we have done in the previous video also, but for the purposes of comparison, let's keep both of them, and we will have an equation of AM also, that is amplitude modulation, right? And we will compare the time and frequency domain pictures, and the code is same that we have seen in the previous video. And here I have taken kf into mt value. Mt is the amplitude of the message signal. So for the purposes of illustration, I am taking it as 0.5 first, right? We will make it 0.001 because for NBFM generation, this kf into mt has to be very less than 1. But first, on purpose, I am taking it as 0.5 so that we understand some concepts, and then we will make it again 0.001. So let me run this code and see the output first, and then we will understand code one by one. So this is the time domain picture, right? So let me zoom a portion of this. So I'm zooming this portion so that we can see this cycle, which looks like one ingredient. So I'm zooming this, and after zooming this, this has become broadened on both of the axes. Now this black signal that you see here is for amplitude modulation. Red one is for NBFM's approximation, and the blue one is the actual FM signal. Now, since the value of kf into mt is greater than 1, but it is not very greater than 1, so you won't be able to see this blue signal showing frequency variations, right? It appears that this signal has same frequency, but actually, since kf into mt is not very large as compared to 1, so this is not being visible, but otherwise it has some very minor frequency gap. In the previous videos, we had seen these blue curves and red curves, they show some deviation, right? Which is also apparent here. Here the red curve is ahead of this, and here the red curve is below of this, right? So now this deviation was apparent there, but the purpose of this code is to compare these blue and red curves with this black curve. This black curve corresponds to AM signal, and you can easily see that with respect to this black signals also, sometimes blue and red curves are in perfect sync, and sometimes they are below, and sometimes they are ahead of this signal. So definitely this black signal is an amplitude modulated signal, linear modulation, and this blue and red signal that you see here for less values of kf into mt, they are also linear modulations, but still they are deviating with respect to it. So it's not that this blue signal will deviate with respect to red only, as we have seen in the previous value. These both signals will also deviate with respect to this black signal also, and that's what I wanted to show you here. Because this deviation of this black signal with respect to this red signal or the blue signal will be used when you will convert this NBFM signal by using frequency multipliers and mixers into uh, higher frequencies, and there this deviation will also be implemented. If you use a frequency multiplier, this deviation will also be strengthened there, the signal will spread. So in that case, the frequency domain representation of the signal will change. So that's what I wanted to show you through time domain. And let's see, for the same thing, you can have this frequency domain picture. So for the actual FM, where we had infinite terms in the series, this spectrum is spread. For NBFM, where we had only 2 terms in the approximation, you can see that the spectrum is the same, but it is clipped off. And then for the magnitude spectrum of AM signal also seems to have the same kind of magnitude spectrum. However, the difference will be there in the phase spectrums. Now, since we have kept KF into MT as very, very less, and there we have made the amplitude of massive signal as very, very less, so we are not able to see the values of these magnitudes magnitudes of message signal here, because we have applied a threshold of zero point 0.7 or something in the previous video to be uh, made as 0 when we plot phase spectrum. So phase spectrum here does not depict correct picture. If you want to see the correct picture, you can keep the threshold as low as zero point 0.1 or maybe lower than that, right? So this is for that purpose. Now let us change the value of this amplitude of message signal to 0.001. Now, what is the use of that? Let's see the time domain picture. Frequency domain picture is less useful for explanation purposes. Uh, but however, in frequency domain, you can see that the sidebands have started to disappear, because now you have made the amplitude of message signal so small that it's not visible here. The sidebands are not visible here. But our main concern was this time domain picture. Now here you can see that these three signals are in perfect sync. The amplitude modulated version, the NBFM approximation, and the frequency modulation actual case, they all are different. They have been created from different equations with different ideologies. Some of them has frequency variations, some of them will have amplitude variations, but taking different approximations in all the three, they all look to be similar. So earlier we said that we cannot identify just by looking at the time domain picture which signal is phase modulated or which signal is frequency modulated, but this is now also true for amplitude modulated signals. You cannot say which signal is which until unless you have a proper analysis done in frequency domain and you have measured some parameters of the signal. So this was one of the purpose of this code. Now let's come to code number C. I'm not explaining this code because this is the same code that we have covered in the previous video. All the equations, etc., are same. So if you have any doubts in this code, you can always leave a comment below my video and I will reply to those doubts. Now, code number C, here we are doing frequency multiplier implementation and we are applying it to a NBFM signal, right? So let's first see the results and then we will understand the code. So now here, again, when I run the code, we first need to keep in mind that I am keeping this value of kf into mt, that is kf into am, as 250 and zero point 0.1. Now still it is not very, very less than 1, but first for the purposes of illustration I will make it 250 into zero point 0.1 so that we can see some important points and then we will discuss them. So first of all, let us see the time domain picture. In the time domain picture, you can see that there are again these three signals: FM actual signal, then you have NBFM's approximation, and then you have NBFM approximation which is clipped. So let me zoom a portion of this complete thing and then we will understand it. So I'm zooming these two waves and let's have a look at these two waves. Now here you can see the blue signal is the actual FM signal, right? Although since the value of kf into mt is not very greater than 1, so you won't be able to make out that frequency is changing between different cycles, but it is there. Now this red signal that you see here is NBFM's approximation. That means it does not have infinite terms, it only has two terms, and because of that you can see that the amplitude of this red signal becomes higher as compared to the blue signal here, and it becomes lower as compared to the blue signal here. And the third signal that we have got is a clipped version of this red signal. This magenta colored signal or this pink colored signal is actually a clipped version, where if the value goes higher as compared to the maximum amplitude of this actual FM signal, we have clipped it. And this clipping happens in these frequency multipliers. Whenever a signal is made as input to that, we do this clipping, because you know this extra red signal that you see here, the extra uh, going down or coming up of this signal, it corresponds to amplitude modulation. We have seen this in this previous code also, where this red signal was showing this amplitude variation, so we want to clip that, so that is why we are clipping it off. And if you want to see amplitude modulation further, let us again increase the value of this from zero point 0.1 to 1. There the amplitude modulation will be clearly visible, although it will not remain NBFM. But let's see, for the sake of explanation, what happens when we do not have this So here you see this now FM is clearly visible here. This blue signal is there, and you can see the frequency variations that this blue signal exhibits, right? Because now we are going for WBFM case. We do not have KF into MT, which is very less than 1. In fact, it is greater than 1 to a substantial extent. Now, this NBFM approximated signal is the signal which has only two terms. Now, you can see that it is showing amplitude modulation. It is showing amplitude modulation also, right? So we need to clip this signal, and the clipped version of this signal is this magenta or pink colored signal, which you can see here. It is the same signal as red signal, but wherever the values are larger than the largest value of blue signal, we have clipped them. So I'm zooming this portion. You can see that this is the maximum value of the blue signal, and we have clipped this signal here, right? So this is what we do here, right? And now let's bring it back to point one, because in frequency domain I wanted to show you something. So let's see it in frequency domain first, and then we will move forward. So in frequency domain, if you see this complete thing, I have plotted magnitude spectrum of FM signal. So this has got this kind of spectrum, right? So it is centered around some frequency, and it has got sidebands. So you can see that the sideband is visible here in form of this little spike and this little spike, and this is reflected here. So that to show these sidebands to you, I have taken KF into MT little bit larger than 1, but in the actual experiment we will make it 0.001 again, the product. Then this is the magnitude spectrum of NBFM approximation. So approximation spectrum is also same, because we said that if KF into MT is less, then in that case these higher order terms will not be there. So NBFM and these will be more or less same. And then magnitude spectrum of NBFM approximated clipped version will also remain same, right? Now what we have done is we have applied this process of frequency multiplication to this NBFM clipped version, and then you see here at frequency omega c, which was the carrier frequency, the signal is already there. At frequency 2 omega c also, this spike and this spike corresponds to that signal. At frequency 3 omega c also, this is there. But as we go higher in frequency, the amplitude reduces. So these things are there till the point we have the nonlinearity order. Means if I have a sixth order nonlinear system, so then we will have uh, till omega 6 times of omega c here, right? And suppose I want to have a signal which is shifted from this particular omega c to twice of omega c, so I can just put the band pass filter here. This green one is the band pass filter which I have kept to begin with at the original position of omega c. If you want to have it at omega c, you can put the same filter at omega c, but you have to make the width of this filter larger, because there the frequency deviation will also be made twice. This is what we have studied in frequency multipliers, right? Not in case of your frequency mixers. Frequency mixers will just shift the frequency. They will not you know make delta f twice, thrice, etc. So that's what we are going to do. So this is the thing. Now we will make it you know actual 0.001, and then we will see the results. So here we have got zero point 0.1. Now I am making it as 0.001, so that kf into mt is very less. And then in this case, if you plot the graph in time domain, you can first of all see that all the signals, they are perfectly matching. No amplitude variation is visible here, and NBFM, FM, and clipped version, they match perfectly, because kf into mt is very less here. So to illustrate that difference, I have taken kf into mt larger than 1 in the previous case, but this is the actual way how things are done in this. Now in frequency domain, if you see, you are only able to see the spikes corresponding to carrier. Why? Because the massive signal has very low amplitude. So it is there, but you are not able to see this numerically. Maybe if you zoom to sufficient extent, you will be able to see that. And here you have got this thing. You have magnitude spectrum of this nonlinear signal. So this nonlinear sixth order or seventh order filter or fifth order filter is used here, and you have got spectrum at all the other frequencies also. And to begin with, I have selected only the signal which was at omega c only. So after applying this band pass filter, I have got this result. This was the actual NBFM approximation, the clipped version. I have forgotten to return this clipped version here. So this was the clipped version, and this is the signal that I have recovered from this particular spectrum after applying the band pass filter. And you can see that there are a lot of variations in this signal in terms of amplitude. Why are these variations coming into picture? These variations are coming into picture because you have applied a band pass filter, and you can see here, wherever this band pass filter is applied, wherever edges are there, this clipping of signal happens here. So that is why you see some amplitude variations here, but they can be corrected by again clipping this signal. You will get a perfect sine signal here, right? So this is how you generate NBFM approximation. Now let us have a look when you want to select a frequency other than this omega c. Suppose I want to select it at twice of omega c or thrice of omega c. So I'm making change in my code, and we will discuss the code of course later. So for n equal to 1, you have selected it at omega c. For n equal to 3, you will select it at thrice of omega c with thrice of frequency deviation. We will understand this code, but let's see the results first. So an application of this, let's see the time domain picture first. In the time domain, you can see these are perfectly matching because kf into mt is not tampered with. In frequency domain, you see that the filter has shifted to thrice of omega c, and here actually you see the filter width is also increased correspondingly. Right now, we can see it in this recovered signal form also. So corresponding to one cycle, you will notice that there are three such spikes corresponding to one cycle. So the frequency of this has become thrice, although the amplitude variations are there and we have discussed that they can be dealt with. So it can be done there. So if you will take the frequency at twice of omega c, the filter will be here with a little less width as compared to this one, and you will receive the final signal which will have two cycles corresponding to one cycle of the original. So this is how your NBFM signal is shifted to a higher frequency with a larger frequency deviation. Now quickly let's come to the code and discuss what all it means. So I will explain the sections in brief, and if you have doubts, we can have another video where we will discuss this code in great detail. So this first section is just for naming. Second section is for sampling. You already know sampling from other videos, how time and frequency axis are generated. And this third video is for defining the message signal. Sorry, the third heading is for defining the message signal and the values of kf, mt, etc. This is also easy. We have done it in the previous video also. Fourth is for carrier signal. Fifth one is for performing FM and NBFM as per their equations. So you can see this code here, and you can download this code from the link which is pasted below my video on YouTube. So this is there, equations are implemented, and then you perform clipping the amplitude modulated signal or the NBFM signal. So this clipping logic is given here, so you can see these equations for yourself. And the non-linear version of the signal that I have created is such that I have got the NBFM approximated signal which is clipped. I have raised it to the power of 6 plus raised it to the power of 5, raised it to the power of 4, and so on up to raised it to the power of 1. So in this way, I have got this non-linear signal, and then I have brought all of the signals in frequency domain by applying FFT and FFT shift. We are also aware of this. And then we have done the band pass filtering. So I have created a band pass filter. These first three lines are for creating the band pass filter and selecting the appropriate frequency deviation. So we know that if we have shifted it to a frequency n of fc, the frequency deviation has to be n of fm. So that is what has been implemented here. You can check these equations also for your code if you will write some. Then I have brought the signal, then I have applied this band pass filter in frequency domain, then I have filtered it in time domain by applying inverse fast Fourier transform and IFFT shift, and then I have applied the plotting logic. So you can understand this code on yourself, and if you have some doubts, you can always post them in the comment. Now the last code, which is very simple enough, is for frequency mixer. So frequency mixer will just shift the frequency of the signal. It won't change the frequency deviation of the signal. So let's first run this code. We have implemented first for DSB-SC signal, and we will also see it for an NBFM signal. So let me run the code first and let's see what happens here. So this is the frequency domain result. I have not showed the time domain expressions here, because they are not useful here. So this is your signal, which is double sideband suppressed carrier signal, and here you have got no carrier, that is why it is suppressed carrier. And this is the magnitude spectrum of the intermediate signal when you multiply it with omega mix. So you have got this. So you have got, I have used omega mix is equal to omega I plus this omega c. So plus sign is used, that is why I have got this signal which is shifted here, and some version of it is shifted here. And since I was interested in shifting it at some frequency, so I have selected that through band pass filter, and after passing it through band pass filter, I have got this response. Notice that the scales here on the y-axis are different, that is why they appear to be very small here. But again, the same signal, when it has been passed through band pass filter, it appears to be big, although the amplitudes they remain same because the scales are different here. So this is how the process should work, and let's have a look at the code first. It's very simple. You have first of all done the sampling theorem for creating the time and frequency axis, then you have defined a message signal, and you have defined a carrier signal. You have performed the DSB-SC modulation simply by multiplying them, and then you have performed the frequency mixing operation by using f mix as fc plus fi. You could either use omega mix as omega c plus omega I, or by using this 2 pi factor you can use this f mix also. And you have created a signal too where DSB-SC signal is there, and you have multiplied cos 2 pi f mix t here, right? So your signal is shifted and the spectrum is shown, you have seen it already. And then you have brought the signals in frequency domain, and then you have applied the filter. This filter is created by the same logic as we have done in the previous code. And again, we have done the plotting, so plotting logic is easy. So now you can see the result again, and you can see that this is the magnitude spectrum for DSB-SC, and when it was multiplied with this carrier which has frequency omega mix, which is a summation of omega c and omega I, you have got this shifted spectrum, applied a band pass filter, and got your signal here. Now here the important thing to note is your carrier frequency has been shifted, but you can see that there is no enlargement or shrinking of distance between these two in the entire process. And that's very important. In the previous method, what happened was carrier frequency was getting shifted, as well as the gap between these two was supposed to increase, and it was increasing or decreasing depending upon whether you have used plus or minus in omega mix. So that was happening there in the previous case, but in this case it is not happening there, because when you perform the operation of this frequency mixing, it only shifts the carrier frequency, and it does not disturb the message signal frequency relative to the carrier frequency. So that's what I wanted to show you. And I have used DSB-SC modulation here because in your textbooks it is illustrated this way. However, this can be applied on NBFM also. So for NBFM also the same code is there. Irrespective of DSB-SC, we have performed this NBFM modulation. So I will just show you the results, and you can see that in the results also for NBFM you have got these three spikes. These three spikes have been shifted by omega mix multiplication, so they have been shifted, applied a band pass filter, and got it here. So the gap between these three spikes is constant everywhere, only that the frequency has been shifted from omega c to some other value, the frequency that we have desired. So this is what I wanted to show you. So in today's lecture, although it was a long lecture today, but I have given you the basic codings for these frequency converters, frequency multipliers, DSB-SC modulator, NBFM generator. Now you can generate this complete system in at least coding, and you have understood the meaning of what is clipping, because every frequency multiplier converter will have associated clipping of the signal. You know why clipping is necessary, because we do not want to have amplitude variations in frequency modulated signal. So what is the meaning of clipping, why NBFM is generated at this particular point, etc. So this is probably it by now for this particular video. And in the next video we will do some more experiments about this complete thing. So till then, thank you very much.